Have you ever really thought about what happens in that split second you tap your phone to turn on a smart light? You've just shot a command across the room. No wires, just thin air. Well, today, we're going to follow that tiny piece of data on its absolutely incredible high-speed journey through the air. It really all boils down to this one simple but surprisingly deep question. We know our devices speak in ones and zeros, right? But how does a one physically leave your phone, fly through the room, and tell that light bulb what to do? That's the mystery we're unraveling today.
Okay, so before we can send our message, we have to understand the language it's written in. And, for all our fancy tech, the native language of every single computer is, you might be surprised, fundamentally simple.
We humans, we think using a system with 10 different symbols, 0 through 9. But computers, they just strip it all down. They only use 2, 0 and 1, off and on. That's it. This is called binary, and it is the absolute foundation for every single digital command.
So you might be wondering, how do you say anything complex with just 2 symbols? Well, you just string them together. Take the binary number 1011. That's not just random, it's a very specific code that our devices know means the number 11. And using this method, literally any piece of information, a number, a letter, a command, like turn on, can be translated into its own unique string of ones and zeros.
And what's actually processing this binary language? Tiny, and I mean microscopic electronic switches called logic gates. The best way to think of them is like the neurons of a computer. They take in binary bits, make super simple decisions based on rules like and, or not, and then spit out another binary bit. Billions of these little guys working together is what lets your phone think.
Okay, so we have our message. It's a neat little sequence of ones and zeros. The next step seems pretty obvious. Just broadcast it with an antenna, right? Well, it turns out there's a huge, and I mean a physical problem with that idea.
Yeah, this is where physics kind of gets in the way. See, to broadcast this signal efficiently, your antenna has to be a certain size that's related to the signal's wavelength, which is basically the physical length of one single wave. And the low-frequency signals that our digital data creates have very, very long wavelengths.
How long are we talking? Well, let's just take a simple 10 kilohertz message signal. To broadcast this thing directly, you would need an antenna that is a staggering 7.5 kilometers tall. That's not a typo. That's taller than most mountains. I mean, imagine a tower stretching almost to where jumbo jets fly.
So the answer is pretty clear, right? It is just not going to happen. It's impossible. So our digital message is all ready to go, but it's completely stuck on the ground. Or is it? This is where human ingenuity really shines. We can't build a 7.5 kilometer antenna, so we had to come up with a much, much smarter way to get our signal into the air. And that solution is an absolutely brilliant process called modulation. Modulation is really the hero of our story. All it means is we take our important but slow, low-frequency message and we make it hitch a ride on a much higher frequency wave. We call that the carrier wave. Think of the carrier wave as a super-fast bullet train that's designed for long-distance travel. Our message is just the passenger.
Let's break that down. So first, you've got your message signal. That's the passenger. It's got all the important info. Second, you've got a high-frequency carrier wave. That's our high-speed bus. It has no information itself, but man, can it travel. Modulation is just the simple act of putting the passenger onto the bus. The final modulated signal now has the brains of the passenger and the speed of the bus.
And the result of all this? It's a total game changer. Look at this. By putting our signal on that high-frequency carrier wave, the antenna we need shrinks from an impossible 7,500 meters down to a completely practical 75 meters. Problem solved. Our signal is finally, officially airborne.
So our signal, riding high on its carrier wave, launches into the air. Now it's zipping across this huge infrastructure of our wireless networks that have gotten unbelievably faster with every single generation.
And that journey has evolved like crazy. 1G back in the 80s gave us those first kind of crackly analog voice calls. Then 2G brought us clear digital voice and, of course, texting. 3G opened up the world of the mobile internet. 4G made streaming HD video in your hand totally normal. And today, our signal is cruising on 5G networks with the insane speeds needed to power the Internet of Things, which, hey, is exactly where our smart light lives.
So in less than a blink of an eye, our signal has crossed the network and it has arrived at the smart light. But wait, the journey isn't quite over yet. The signal still has to be caught, understood, and, acted upon.
Because inside that light bulb or your smart thermostat, there isn't a big, powerful computer like the one in your laptop. Nope. It's something much smaller, way more efficient, and super specialized. It's called a microcontroller. And the key difference here is focus. A microprocessor in your PC is this powerful generalist. It's designed to do a million complex things at once. But a microcontroller? It's a specialist. It does one job, like turn a light on or off, and it does it perfectly, cheaply, and using barely any power. It is the perfect little brain for a smart device.
And this is it. This is where the whole journey comes full circle. The microcontroller grabs that radio wave and it performs demodulation, which is just the reverse of what we did earlier, getting the passenger off the bus. It pulls out that original binary message. It executes the command and, boom, the light turns on. A simple command became a signal, and that signal became a physical action in the real world.
From a simple binary code all the way to a real-world action, this incredible, invisible journey is happening billions of times a day, all around us. The technology is mind-bendingly complex, but the result is a world that just works seamlessly. Now that you've seen the path one little signal takes, it really makes you wonder, what incredible journeys is your data taking right now?